Welcome to Contendo Training Solutions Fundamentals of Steam-Assisted Gravity Drainage training course for bitumen processing. Contendo also offers Fundamentals of SAGD courses covering SAGD well pads, produced water de-oiling, and water treatment. Our unique presentation of learning material provides something for all types of students, whether their strong suits are listening, reading, or watching. We combine narrated discussions with animations and other visuals to clarify each concept presented. Straightforward learning objectives are presented at the beginning of each chapter, while review sections reinforce what we have discussed. The steam-assisted gravity drainage process is a leading in-situ bitumen recovery technique. We discuss all aspects of bitumen processing in a SAGD facility, from recovered emulsions to sales oil. We describe the technologies and processes used to safely produce saleable oil from reserves of bitumen recovered from the oil sands. The purpose of a SAGD facility is to safely and economically produce sales oil with specific vapor pressure, water content, API gravity, and viscosity. You will follow the bitumen as it flows through a model SAGD central processing facility and learn how it is processed from a high-pressure mixed emulsion of bitumen, water, and hydrocarbon gas to oil, meeting all sales oil specifications. We use a combination of narrated animations, text, and other visuals to demonstrate how a process operates. We start with diluent heating and injection into the produced emulsion for density adjustment of the bitumen.
Note that several downstream process vessels produce hydrocarbon condensate, which can often be recycled and used as diluent.
We follow the produced emulsion through the bitumen inlet section of a SAGD central processing facility where bulk separation of oil and water occurs in a free water knockout. The resulting produced emulsion diluent mixture then has most of the remaining water removed in an electrostatic treater to produce dehydrated dilbit. The dilbit flows through the sales oil stabilization system gas boot where it is reduced in pressure to bring it to sales specification. The separated hydrocarbon vapors are processed through the gas handling section of the stabilization system to produce fuel gas and hydrocarbon condensate. The sales oil is then stored until it can be transferred to the sales pipeline. We also follow the separation and recovery of produced gas from the produced gas separator, as it is processed for use as fuel gas in steam generation. Oily produced water and hydrocarbon liquids are removed and directed to their respective process trains. The produced gas joins other gas streams in the mixed fuel gas separator for liquid removal before being burned in the steam generators. Accumulated unbroken emulsions, called rag layers, are removed from separation vessels and tanks and processed through the flash treater to vaporize any remaining water from the dilbit so that it can rejoin the dehydrated dilbit flowing to the stabilization section. Hydrocarbon vapors from the flash treater are processed through the flash gas system to produce fuel gas and hydrocarbon condensate. A vapor recovery unit collects and processes various usable gas streams to produce fuel gas and hydrocarbon condensate. We include appropriate pressure safety valves throughout the entire process and include a gas flare system to accept and burn relief vapors and purge gases. Detailed descriptions of process control systems show how certain parameters up or downstream can affect local conditions. Control logic set points and commands explain how out-of-range process conditions can be dealt with, and comprehensive shutdown responses are demonstrated to show the relationships between various system components. Here, we show a vibration transmitter on the VRU compressor, and how a high vibration will alarm, tripping the compressor motor off to avoid damage, and simultaneously closing a gas recycle valve, the PV, and opening a compressor ring water bypass valve, the XV. In this course, we discuss safety points relating to protection of personnel, equipment, and the environment, how gas vapors are removed and processed for use as fuel gas so that the bitumen meets sales oil specifications for vapor pressure, how water and water vapors are removed so that the bitumen meets sales oil specifications for water content, and how diluent is added so that the bitumen meets sales oil specifications for API gravity and viscosity. Here is an excerpt from our free water knockout chapter that demonstrates our presentation.
Heated diluent, reverse demulsifier, and demulsifier are added to the produced emulsion to enhance the oil-water separation process. The diluent and chemicals are completely blended into the emulsion in an inline mixer. Slop oil may also be routed to the free water knockout inlet stream on a batch basis. This is done to recycle the hydrocarbon liquids from the slop tank as required. Chemicals are added to the inlet stream to enhance oil-water separation throughout the process. These include demulsifier and reverse demulsifier. This is an important chemical process that accelerates oil-water separation. Reverse demulsifiers will cause the oil droplets suspended in the produced water to coalesce, so they will rise to the surface. As they are water-soluble, they will more readily mix with the produced water contained in the inlet stream. Demulsifiers promote coalescence of the water droplets in the dilbit to form larger droplets that fall out of suspension. Heated diluent is injected downstream of these chemical injection points to reduce the density and viscosity of the emulsion's bitumen component. This aids in separating the bitumen from the produced water by increasing the density difference between the two and allows shipping of the bitumen via pipeline by meeting the sales oil density specification. Remember, if diluent is not added to the bitumen, the sales oil at the end of the process would stop flowing as soon as it's cooled below its pour point temperature, where a liquid becomes semi-solid and loses its flow characteristics. Generally, the diluent to free water knockout flow control scheme will take into account the production flow rate downstream of the free water knockout after removal of produced water to determine the diluent injection rate. The mix feed stream is introduced into the free water knockout through an inlet diffuser. A series of internals within the vessel promote the gravity separation of the dilbit and water. The internals include various deflectors, baffles, and packing to direct the flow and enhance coalescence. Note that each installation will differ. The produced emulsion separates into a layer of wet dilbit in the upper section and oily produced water in the lower section, with a rag layer between them. The wet dilbit overflows a weir and collects in an oil box located in the outlet end of the vessel. From the oil box, the wet dilbit is routed to the treater feed coolers for cooling before proceeding to the electrostatic treater for further processing. This dilbit flow is controlled to maintain the oil box level. Produced water is drawn off the bottom of the vessel under interface level control. The produced water is sent to the produced water system. This process is discussed in the produced water de-oiling course. A rag layer of unbroken emulsion accumulates over time and will impair separation at the oil-water interface. This is inherent in the process and requires management to minimize its effect on the process. To minimize the accumulation of a rag layer, a portion of it is drawn off at the interface level and recycled back to the inlet stream of the free water knockout for further processing. If the rag layer continues to accumulate despite recycling, the rag layer may have to be drawn off to the slop tank for further processing.
This gives you an idea of how we discuss process through system vessels. As you progress through the course, you will see various warnings and safety points associated with the topic being discussed.
These can be represented as safety points to denote specific safety hazards and/or equipment used to mitigate the hazards, cautions to bring attention to possible hazards, or reminders to review material safety data sheets.
We use various graphs and charts to explain hazards such as hydrogen sulfide concentrations. Here is an excerpt.
H2S is colorless and flammable, with specific odor characteristics depending on the concentration. At low concentrations, less than 1 part per million, it has a very identifiable rotten egg smell. This odor gets stronger in concentrations up to approximately 30 parts per million. Between 30 and 100 parts per million, the odor becomes sweeter. Above 100 parts per million, the concentration paralyzes nerves, causing a loss of the sense of smell. At this point, you can be easily overcome by the H2S without smelling anything. At H2S concentrations above 200 parts per million, even a few breaths can cause collapse and death due to respiratory failure.
Formulas are used occasionally to prove concepts, such as this excerpt explaining gravity separation rates.
Here is the modified Stokes Law as a formula. The modified Stokes Law states that the velocity of separation, v, is equal to the density difference of the two phases represented by d1 minus d2 times the square of the size of the dispersed particles r squared times the gravitational constant c, all divided by the viscosity of the continuous phase n1. All of the variables in the formula influence separation. To make the phases separate faster, we can increase the difference in density, decrease the viscosity of the continuous phase, or increase the size of the droplets to be separated. However, the greatest impact is the size of the particles or droplets to be separated because the relationship is not 1-to-1, but instead is the square of the size. This means that as the droplet size doubles, the separation velocity is increased by 4 times. As size triples, the separation time is 9 times faster. As size quadruples, the droplet separates 16 times as fast, and so on.
Chapters include printable worksheets for students to complete as they learn and individual tests that can be attempted after viewing each chapter. Try the Contendo Fundamentals of SAGD Bitumen Processing course and you will receive the best comprehensive process training available. Come on and see for yourself.